Assalamu alaikum. Good morning, everyone. First of all, I would like to thank the Research and Innovation Development Authority for the invitation, for their hospitality and the excellent organization. Thank you all for coming. Second, I would like to apologize in advance if after the talk the title seemed a bit misleading. You see, the plan was originally to try to convince you that using data-driven evidence that quantum isn't a hype by presenting VC funding, history, government funding, the startup ecosystem, the initiative, and projects around the world. Then the plan was to try to convince you that by demystifying some of the quantum technologies, and that the clearing the fog part of the title. So, but I only have 15 minutes, so with that being said, this is my best attempt. So let me present to you the Exhibit A. This plot shows the amount of VC fundings and quantum startups over the years, up to 2022. It's 2 years old, but I believe the trend still holds. And you can clearly see the upward trends in the last few years. In fact, the last year alone, the amount of funding in quantum startup almost amounts to all previous years combined. And to put that into perspective, I've compared it with two other transformative technologies, namely AI and cybersecurity. And in quantum, by 2022, the amount of investment, this is the cumulative plot, by the way, cumulated up to $3.8 billion in investments. This milestone was reached by AI in 2013 and by cybersecurity in 2006. So think about it. Quantum today, or 2 years ago rather, was in the same spot that AI was in 2013 or cybersecurity in 2006. So ask yourself this question: what would you do knowing what you know now about AI in 2013 or cybersecurity in the early internet age? I think that's the same question government have been asking themselves, as Exhibit C here clearly shows, with the billions of dollars in investments in quantum tech, with China and US and UK leading the race. This, ladies and gentlemen, is not a sign of a hype. This is a sign of a global race. And why the excitement, you might ask? Allow me to explain with a simple example, with something I'm sure you're all familiar with, timekeeping. Take, for example, a mechanical clock. Even the most accurate mechanical clock with the most advanced movements in the likes of Rolex and Patek Philippe or whatever, their accuracy is about plus or minus 1 second every 4 hours. Going from mechanical to digital, the accuracy jumps to 1 second every year. Now, going from digital to quantum, if you have an atomic clock, the error rate is plus or minus 1 second every 30 billion years. That's 30 billion X improvement over digital. That's, ladies and gentlemen, is not a simple jump. That's a quantum leap, pun intended. Another miracle of modern science is, if you think about it, MRIs. MRIs allows doctors to pierce through tissues to reconstruct a 3D image of the brain without touching you, let alone poke a needle. That's the promise of quantum computing. That's the power of quantum computing that enables such technology. And these are examples of quantum sensing devices, but the real excitement is in the next frontier, quantum communication and quantum computing. So what is quantum exactly? Well, it's third of physics, or third of reality, as I like to call it. We're all familiar with classical physics. We've all studied it in high school and undergrad. We've studied phenomena such as the laws of motions, electromagnetism, gravity, etc. And you can argue that the more we understand physics, the more we understand reality, the better technology we can develop. You couldn't develop a car, for example, if you don't understand the interaction of forces, the laws of motions, gravity, etc. And as you scale up, the laws of physics change. You start exiting Newton's territory, entering Einstein's world of relativity, and you encounter new phenomena like time dilation, constant speed of light, length contraction, the interstellar realm, if you will. And these can only be explained by Einstein's general theory of relativity and special theory of relativities. And again, the more we push the boundaries of our understanding of physics, the better technology we can build. Take GPS, for example. GPS depends on accurate timing signals, and time depends on speed, special theory of relativity, and gravity, the general theory of relativity. And believe it or not, if it wasn't for Einstein correction factors, the error rate of GPS would accumulate at 10 kilometers per day, deeming GPS basically useless. So you can argue that relativity physics enables much of space technology we have today. And similar, as you zoom into the microscopic world of Schrodinger, Heisenberg, Bohr, you encounter new phenomena that neither Newton nor Einstein can explain, such as superposition, the entanglement, the wave-particle duality, etc. So in a nutshell, what quantum technology is basically utilizing quantum phenomena to fill in the blank, to measure data, that's quantum sensing, to transmit data, that's quantum communication, to manipulate data, to process data, that's quantum computing. So in the next few slides, I'll try to demystify each of those phenomena and provide a computational example. So our first culprit is superposition. We're all familiar with how classical information technology represents information in a binary form as 0 and 1. Physically, it's implemented as a transistor, either passing a current or blocking it. In the old days, it was vacuum tubes. There can be either on or off. You can use any binary system for that matter, even coins, 0 or 1. But you can also use subatomic particles. You can use the spin of an atom to encode as 0 or 1, spin up being 0, spin down being 1 in this example. But what's different about quantum objects is that they can be in a third state, a superposition state of 0 and 1. And now, instead of having a classical bit, we have what is called a qubit, the smallest unit of information in quantum information science. And when this qubit is in this superposition state, any operation on it will affect simultaneously the 0 and 1, right? So, and by extension, if you have 5 qubits in a superposition state, effectively you have data that represents all possible 5-bit strings, from all zeros to all ones and everything in between. And every operation you do on it, it will affect all possible combinations at the same time. Let me demonstrate with an example. So say you want to multiply 2 numbers together. Okay, in a classical computer, you would have to do it sequentially. You would multiply 0 by 1, you get a result. You multiply 1 by 0, then you multiply 0 by 1, and then you multiply 1 by 1, and you get a result for each. In a quantum computer, what you do is you put the qubits in a superposition, let the quantum computer run the calculation, and it will multiply each possible combination together at the same time. But what's interesting, the result is another qubit, which is in a superposition state of 75% 0 and 25% 1. You might ask yourself, what does that mean? Well, it reflects the classical result, because the classical result is 75% 0 and 25% 1. So this is not the end of the story of quantum computer. After the processing, you need to measure the qubit, and that's the realm of quantum algorithms, basically. Sometimes it's scaled linearly, sometimes scaled exponentially, so it's not always a single-step process, unfortunately. So that's superposition. Our next culprit is the measurement problem. As I said, in quantum computation, it depends how you measure, it depends how you look. So let's say you had prepared the qubit in a horizontal state, right? It's pointing towards the east. If you measure it vertically, the qubit has to align itself with the measurement axis. It just has to. In this case, it will do it randomly, either up or down. Okay. Similarly, if it had been prepared vertically and you measured horizontally, it would have to align itself horizontally. But if it just happened to measure along the axis of the qubit, then the result will be deterministic. If it's vertical, it will stay vertical. If it's horizontal, it will remain horizontal. So notice the slide now. The results on the left are the same. The results on the right are the same. So just looking at the qubit, you wouldn't know whether you got a random result or the correct result, unless you know how the qubits was prepared in the first place. So how can we utilize this computationally? One of the big promises of quantum communication and computing is what is called blind computation or secure quantum computation. Imagine a world where you can send your query to OpenAI encrypted, OpenAI process the query encrypted, return the result to you encrypted, and only you can decrypt the data. That's what's called blind quantum computing. Allow me to explain how it works. It's very simple. Say Alice wants to multiply 0 by 1. Instead of sending classical information, she would encode it as qubits, as up and down, send it to Google, Amazon, OpenAI, whatever. They can run the calculation, but the result will be a qubit. So if Google doesn't know how the qubits were prepared, they might measure it incorrectly and just get a random result. Because Alice should have just easily prepared it in the horizontal state, and in this case, if the cloud measured vertically, you would get a random result. So unless you know how the qubits were prepared in the first place, you cannot read the results. The third phenomena is entanglement, probably the most famous and the most misunderstood. An entanglement is a strong correlation that quantum objects can have, where in the case of spins, before measurement, they don't have a determinate spin before you measure. But once you measure one, it will collapse, and the other one would collapse with the opposite spin instantaneously, faster than the speed of light. And I should stress, it's faster than light correlation, not causation, because otherwise it will violate the theory of relativity. But we cannot use entanglement to transmit data faster than the speed of light, unfortunately, but we can still do awesome things with it. One example is what is called super dense coding in quantum communication. What super dense coding promises is that you can send 2 bits for the price of 1. Okay, here's how it works. Alice and Bob pre-share entangled pairs, okay? And if Alice wants to send 0, 0, she just sends her qubits unaffected. If she wants to send 0, 1, she would apply a 90-degree rotation and send the qubits. Then Bob will get 0, 1 in this case. If she wants to send 1, 0, she would apply a 180 rotation. And you guessed it, if she wants to send 1, 1, she would apply a 2070-degree rotation and send the information. Notice that Alice only sends 1 bit, but yet Bob was able to read 2 because of the entanglement. Third phenomenon is the wave-particle duality. Now here's a mind bender. You know you can let less light in by opening more windows because it makes sense, it's counterintuitive, but it makes sense if you think of light as a wave, because waves interact with each other and cancel each other out, and which is beautifully demonstrated by the most famous experiment in physics, arguably, the double slit experiment. If you bring a light source and shine it to a double slit, what you get is an interference pattern. Intuitively, you would think you would get 2 straight bands, but actually the brightest spot is in the one in the middle, in between the 2 slits. Which, if you think of light as a wave, makes perfect sense, because when light interacts, they either cancel each other out or constructively interfere. However, if you try to measure anyway where the photon went, in which slit, then it starts to behave like particles. You would see the classical results. Here's a simple experiment where you can utilize the wave-particle duality in sensing. Here's the recipe. Bring 1 laser, 2 mirrors, 2 50-50 beam splitters, and 2 detectors. And let's apply our classical thinking first. There are 4 possible paths photons can take. They can either pass through the first beam splitter, reflect through the mirror, and then pass through the second, or reflect through the second, or reflect through the first, pass through the second, or reflect by both. 4 possible paths, 4 all equally likely, then you would expect the detectors to click with 50-50% probabilities, right? That's the classical explanation. Now let's think quantum mechanically. Light will travel as a wave, it will hit the first beam splitter, and then it will not go either left or right, it will go in both paths at the same time in a superposition of these 2 paths. And then it will re-interfere with itself in the second beam splitter. And if you do the calculations right, it can exit either the B path, and it will be out of phase, and it will cancel each other out. So you'd expect 0 detection rate at this detector. Or it will be in phase and constructively interfere and increase the intensity. You would expect 100% detection rate at detector A. And guess what? Quantum mechanics is right. That's what you observe when you apply this experiment. And if you think about it, what you have in front of you is a very sensitive quantum device that's sensitive up to the wavelength of light. Because as you change the distances even ever so slightly, if you shift by a half a wavelength, the distribution will shift from all the way in phase to out of phase in detector B. I'm almost out of time. If you allow me more 2 minutes, or feel free to stop at any time. Anyway, so I'll skip this experiment. The second or fourth phenomena is quantum tunneling, which should be of interest to the quantum machining crowd. I was given a signal to finish the presentation. Anyways, So I'll just skip through the end, and here is a summary of the quantum phenomena, how can it be utilized computationally, if you'd like to take a picture or anything. And thank you all for coming, and appreciate it. Thank you very much.